Hello and welcome back to Calculus 2. This is the review for exam 2 coming up in 2 days. So we have chapter 7, which is integration. Now, you cannot lose the sense of basic integration and U sub. They are still two primary integration techniques. So, basic integrals plus U sub, yes, both are studied in Calc 1, but they are absolutely necessary in everything we do. And then we have by parts. One problem, obviously. We have the trig sub. Note that when I ask a trig sub question, you are necessarily doing the trigonometric integral, right? So technically those two sections, 7.3, 7.4, they fuse into one. I don't have to ask a separate trig question. Number 4, partial fraction. And this is where I said two problems. Solve 2 by 2 or 3 by 3. Set up, I don't know, larger than 5 variables, I would say. I don't know. It's a whole bunch of things I put there, and then you just make the setup with A, B, C, D, you know, how many you need. By parts, maybe 1 or 2. Well, you definitely have 1. I mean, it has to be on the test. It's just if I have an extra problem, it's gonna probably be by parts. The next, remember that other means of integration. I can't give you the chart, so 7.6 is out for testing. But then we have numerical. And you guys are responsible for formulas. You must learn. That's your Calculus 2. You learn the formula for by parts. You learn the procedure for trig sub. You learn the procedure for partial fractions. You memorize the formula for 3 numerical integrations. The midpoint, the trapezoid, and the Simpson. Now, there's going to be one problem. So it's not all 3. It's going to be one of those 3. You also have to remember that n is even for Simpson. And you remember the midpoint averages the points. The trapezoid has the pattern 1, 2, 2, 2, 2, 2, 1, and then pattern for Simpson 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. Number 6, we have improper integrals. 2 problems. We have type 1, type 2, right? So type 1 easy to see, definitely has infinity in the limit. Type 2, evil, right? Because the asymptote could be on the end, but could be also buried inside. We said that when you learn the improper integrals, your definite integral changed forever. You always now scouting. Anytime you see limits, any math course, any engineering course, as soon as you see definite integral in any course from this point on in your life, is going to be asymptote hunting, right? Because most of the time they diverge if there is an asymptote either at the end or in the middle somewhere. Most of the time, not always, but most of the time. And as engineers, you must be detecting those. Otherwise, you are doomed. So you have to know that. So 2 problems, type 1, type 2. Type 1 easy to see with infinities, type 2 not so easy to see. Problem 7, differential equations. I am primarily interested in two things in there. I am interested in separation of variables, and I'm interested in linear first order, that formula, whether you do it by separation or you memorize the formula, whatever. The graphing problem, I'm not too keen on that one. You will be dealing with that problem when you take differential equations class, and you will be dealing with that problem in slope fields when you take Calculus 3 in chapter 14. So there is really no need in Calc 2 to go crazy with slope fields, which is the graphing problem with those little lines and so on. What did I just say 3 times? Okay, good. So, separation of variables. And I'll make a problem for you, especially. It's going to be, yes. So you're going to get a green test, and on it there will be a problem with graphing, in addition to all other problems. So, yeah. Well, life is not fair. We have to learn that, right? Sometimes when you're too smart, things just happen. So too smart for your own good. So separation of variables and linear first order, which is the equation. So those are the two possibilities for this. Now you see 7 things on the list, but you have 2 partial fractions, right? So that's 8, and 2 for improper integrals, so that's 9. So the 10th problem could be coming from either by parts, could be differential equations, but most likely all trig sub, right? So you have a trig sub and then trig integral that maybe uses u sub or something like that. So there they are. That's the review in terms of the list. Exam is, again, whether it's going to be a replacement question depends on the spiciness of the questions. The exam is designed, again, hour, 20 minutes. We can stretch it out 25 or so. There will be lecture 8.4 after that, which you really do not want to miss. 8.4, we are going to talk about divergence. We're going to talk about integral test, P-series, and no, those 3. But it's the integral test is the one that you don't want to miss. So
we're going to see class first and then the test?
We do the test first and then the lecture on 8.4. You do not want to miss that 8.4 because of the integral test. Yes?
What time do you think you'll start the lecture?
As soon as possible. Generally we run 10 minutes late, so plus hour 30. So as soon as possible. Yeah. All right. So questions, concerns regarding the test, any problems that you would like to... This is the time for you to ask questions and me to provide answers. And then on Wednesday we swap the roles. Yes? Yes, which one?
That one, the setup for the partial fraction, you said 5 variable?
Or 6 or 7.
Can you just do an example?
Yeah. We have a trig sub question first. There's a text. Diego has a textbook over there. Yeah, you have to give me the exact problem you want me to work out from the textbook or homework or something, because I'm not making up problems now. I'll be making up problems tomorrow for Wednesday.
Tomorrow? Or like 5 minutes before tomorrow?
Or maybe Wednesday morning too, I don't know. Tomorrow is Tuesday all day.
page it was on, but we did problem number 56 in the notes.
Well, if it's in the notes, it's in the notes. You want me to redo it?
Yeah.
Because I can quickly jump to trig sub and find 56 on the list. There's 12, there's 21, 28, there's 56. You can download it from the, if you want to study it. It was spicy. You take the textbook and find a problem, something that it's not done. Time for you to ask a problem.
Oh.
Your problem was a partial fraction, if I remember. It's going to be from now on first come first served basis. Whoever has the problem that I can actually write, and well, that's going to be done first. Alright, so x squared plus 3x plus 2 divided by x. Ooh, that cannot be plus. Actually, that's a different one because I remember there was a 4 and 8.
Yeah.
Alright.
I can find that one if you want it.
So the first problem we're going to do is this one. Is the partial fraction decomposition problem, and this is the one that you can actually solve on the exam because it's going to end up being 3 variables. Right? We see that we cannot factor this any further, so we are going to set it up as a over x, that's a linear term, plus bx plus c over x squared plus 2x plus 2 dx. So we make the setup there. It's already factored for us. And we have a linear term, and then we have non-reducible quadratic. Now, once we are done with this, we cross multiply, so ax squared plus 2ax plus 2a plus bx squared plus cx is equal to x squared plus 3x plus 2. So that's our the first one. Now a plus b times x squared plus 2a plus c times x plus 2a, right? Equals to x squared plus 3x plus 2. A plus b is equal to 1. 2a plus c is equal to 3. And then 2a is equal to 2. From there, a is equal to 1. And if a is equal to 1, then b is equal to 0. And if a is equal to 1, c is equal to 1. So you just find your way quickly through equations. So by last equation, a is equal to 1, plug in the first equation, 1 plus b is 1. Well, b has to be 0. And then in the second one, 2 times 1 is 2. 3 minus 2 is 1, so c is 1. And we immediately plug that in our integral. It is a is 1, so 1 over x, plus now b is 0, so that would kill that bx term. And we have c is 1, so it's 1 over x squared plus 2x plus 2 dx. Great. How do we solve this integral here? Complete the square. Yep. So that's going to be tricks up there. This is really evil question. So to complete the square on x squared plus 2x plus 2, I take the 2x, I say the 2 in front of x, I cut it in half and square it, So it's 1 plus 1. So I can break this into 1 plus 1 and just solve this as x plus 1 squared plus 1. And that gives me, so the integral of 1 over x dx is the first one, plus integral of 1 over x plus 1 squared plus 1 dx. And now we need the trig sub. So this is actually good that we are reviewing trig at the same time. So these are legs. So x plus 1 goes here and 1 goes here. And over here I have a square root of x plus 1 squared plus 1. I circle towards the number. Create my red equation as tangent theta is x plus 1 over 1, from where x plus 1 is tangent theta, x is tangent theta, and dx is, tangent theta minus 1, and dx is secant, by derivative of tangent is secant squared theta, d theta. Well, that was quick. The blue equation is going to be a cosine theta, which is the square root divided by 1. And to plug this in, we don't need the square root. So because square root is equal to cosine theta, then just x plus 1 squared plus 1 is cosine squared theta.
Excuse me. Over there, the triangle, what do you wrote? The square root of x plus 1 is square plus 1. Why the square root?
Because the Pythagorean theorem. You square this one plus the square of 1 under square root. It's a Pythagorean theorem. You must have the square root there. That's given. What's the integral of 1 over x dx? What's the integral of 1 over x dx? Ah, there we go. Yeah, these absolute values are not here for decoration. Oh, really? Oh, really? Okay, yeah. Yeah, it's wrong without them. Okay? You did. You didn't put the absolute value. Plus the integral of dx is secant squared theta d theta, and the denominator is cosine squared. Is this right? No, this is not right. No one said anything. This is 1 over square root. And then the square root is the secant. And it becomes secant squared, yes. So it's a secant squared, which is much better because now they cancel completely. And we have ln absolute x plus integral of d theta is just theta plus c, and that's ln absolute x plus, and now theta can be inverse tangent of x plus 1 plus c. Yay! What a problem!
I'm sorry, how do you get tangent?
Inverse tangent? Well, you can solve, you need theta, right? But you are not allowed to keep theta because the integral was in terms of x. So you have to replace this theta in terms of x. Now you can solve tangent for theta by inverse tangent, and theta stays alone, right?
Okay.
Or you can solve and do the cosine of 1, right?
Oh.
But tangent was easier, so we did tangent. Was good? Nice. You had the problem in the book? Well, this was a very nice problem because we got to review the trig and the trig sub and the partial fraction decomposition in one problem. Bravo. That was a very good choice. You know what they say, that 2 birds with 1 stone? This was 3 birds with 1 stone. It's amazing.
3.5.
You're looking for the setup problem?
Yeah, the setup problem. You said that one with.
Oh, the setup problem for the partial fraction decomposition. So, looks like this. So that's how the problem would look like. Now, whether I'm going to type blah or not, I don't know. Because you're not solving this, so you don't need to know what's up there. It doesn't matter. You are simply setting this up as a over x, that's linear, plus b over x minus 1, plus c over x minus 1 repeated, plus now dx plus e, because this is quadratic, and then you have one more for repeated quadratic and you're done. fx plus g over x squared plus 3x minus 1. And there you go, done. I don't know. It's a partial fraction decomposition. 6 points is enough. 1/8, bump to 10. So 1, 2, 3, 4, 5, 6, 7 variables in this particular one. That's your, ooh, shiny. Nice question. 2 to infinity, 10 divided by x ln x dx. Look at that. What happened? Yes, it's a u sub. But before we do u sub, we have to do what?
Well, can we solve the integral and then put the limit for the infinity?
No, we put the limit first.
Because you have to write that even though, I mean, just when we're going to solve that.
Minus 1, minus 1, minus 1, minus 1 for each limit you miss.
But if we just solve the integral and then just. Okay.
You know. This is the most terrible class ever, right? You open? All right. So now, very good, guys. You already solved this. U is ln x, and then du is 1 over x dx. And that quickly solves the issues. So limit b goes to infinity, 2 to b. We'll go back to variables. You have your 10 still up there. U and du. Can kick 10 in front of the limit. And this becomes ln of u, but it's ln of x. I don't need the integral anymore. It's just ln of x from 2 to b. Do we see the divergence? Because when you plug in b, it will be ln, forgot the limit, and it's the points there. Limit b goes to infinity, we have ln of b minus ln of 2. Now, ln of 2 is okay. It's going to be some number, and then you take ln of that. So that's going to be, 1 point some. But this one over here goes to infinity. So, divergence. Now, how do I know that it goes to infinity? Because I know ln graph. See, ln graph looks like this, goes through 1. And as x goes to infinity, you see that the y value goes to infinity. So when I plug in ln, right, when I plug in this infinity here, then ln of infinity is infinity, and then another ln of infinity is still infinity. So they all go to infinity, and it's divergence. It's infinity minus a number. ln of 2, nested. So
also one of type 2.
I'm just calculating ln of 2 is negative 0.3665. So infinity plus 0.3665.
What is the 10?
Times 10 doesn't matter, right? Times infinity. So yeah, 10 should be there.
It would be minus 1, right? You missed the 10.
Oh, it would be minus 1? Well, luckily in this case, no, because I probably wouldn't see it because it's divergent. But if this was converging to 1, or let's say converges to 6, and then that 10 would make it 60. So because it diverges, I wouldn't notice that one. So probably we'll get a free ride on that.
I got an easy one that I want to ask.
Yes.
I don't know how to choose which one. Okay, so integral of sin x, cosine x, dx. We use sub, but how do you know which one to choose?
Oh, it doesn't matter.
It doesn't matter.
It does not matter in this
Doesn't
case.
it give you a different answer?
It gives you the same answer.
Give you the same answer.
That's all. So u equals sine x because du is equal to cosine x dx. You have the integral of u du, which is u squared over 2 plus c, which is a u squared, so it's a 1/2 sine squared x plus c, right? If you choose the other one, u equal cosine x, then you get your du to be negative sine x dx, and your integral then becomes, so this is way 2 now, your integral becomes negative integral u du, which is negative u squared over 2 plus c, which is negative 1/2 cosine squared x plus c. See? Same.
So we saw one example of type 2 integral.
Just find it. Over here, if you are still bothered by this not being exactly the same, realize that the constant, right? But the constant over here, right, has +1 in it. And the 1 is the one that you have sine square plus cosine square is equal to 1. So you have endless supply of cosine squares and sine squares within this constant over here. So that's why and these are the same problems, same solutions to they look different, but they're the same. You found the type 2, you said?
That's 7.8.
7.8, yes. Page 580, 579, 580.
You have one over there, can you pick one?
Pick one. Just. I'm actually looking at the table of contents. I'm not looking at the problem. I see that differential equation start on 581, so I'm saying 579 just by looking at that.
Okay, the integral from negative infinity to infinity of e to the x, I mean x to the e.
X to the e?
No, s e.
I thought we did this one.
X
X
to the negative.
Negative x squared dx, like this. I thought we did this one actually. No, we did this one. I know I did something. All right, great. All right, so we have a problem that has negative infinity and positive infinity. So we have to use Calculus2 theorem that says that this definite integrals can be broken anywhere in the domain where the limits are, right, a to b. So we can choose to break it at 0. So negative infinity to 0 plus 0 to positive infinity. And we are getting two integrals, but the good thing is that the integral is the same. We will just have to deal with the different limits. But you solve one integral and it's immediately the second integral has the same stuff. So the first one is the limit a goes to negative infinity, a to 0, x e negative x squared dx, plus, and we have the limit again, b goes to infinity, 0 to b, x e negative x squared dx. Now, to solve the integral, what do we use? What solves this integral? U sub. That's the easiest. Because you have this exponent negative x squared, and that becomes negative 2x dx, right? So all you need is a negative 2 and negative 1/2 in front. So you can kick that negative 1/2 in front of the limit. And now the limit becomes a to 0. And you have e to the u du. Now the second integral is the same. It just has its own b goes to infinity, and then 0 to b, e to the u du. Now this is negative 1/2 limit a goes to negative infinity, and now the integral is e to the u, so e to the negative x squared computed from a to 0, minus 1/2 limit b goes to positive infinity of e to the negative x squared, 0 to b.
Negative 1/2 minus the negative 1.
They're both negative.
Yeah, but aren't you supposed to subtract the other?
No, that's by parts. These are two separate integrals. So now the first integral has negative 1/2 limit a goes to negative infinity, e to the 0 is 1 minus e to the negative a squared. So that's when you plug that in, and then minus 1/2 limit b goes to infinity, and we have e to the negative b squared minus 1. All right, so this is negative 1/2. And now when I plug in negative infinity and squared, it becomes positive infinity, and then the negative here, negative infinity. So e to the negative infinity is 0. So this goes to 0. This one will go to 0 as well. So we have negative 1/2 minus, and this over here is negative 1/2 plus 1/2, and we get 0. So plug in 0. That's it. Anything else? Some separation of variables, or something with the formula. So and the linear equation, so problem 21 through 24, 17 to 20, (31 to 34), and also 35 through 40. They're also separable. Why do they have? Oh, this one has initial value. Okay. Anything else?
So the final answer is 0 for them?
Mm-hmm.
The C? No? No C? Converges to 0?
Guys, just, yeah, converges to 0. Yes.
7.4 for number 35.
7.4, number 35. Oh, that's the 35 is the what we did earlier, the completing the square. You have dx divided by square root of 3 minus 2x minus x squared. So you have minus x squared minus 2x plus 3. You factor out negative, you get x squared plus 2x minus 3. And then you have negative x squared plus 2x, and then you need plus 1, and then minus 1, which will make this minus 4. And then this is completed the square here, so minus x plus 1 squared, minus and minus will make it a plus because you have minus in front. So this integral converts into square root of 4 minus x plus 1 squared. And then you have your trig sub set up there because you have a subtraction, which means 2 goes here, and x plus 1, you can put it there, which means that this is going to be square root of 4 minus x plus 1 squared. You have your red and your blue. Red is sine, so sine theta is equal to x plus 1 over 2. So x is equal to 2 sine x, so sine theta, sorry, minus 1, and dx is 2 cosine theta, d theta. And for the blue equation, you have a cosine theta, which is the square root divided by 2. So square root is equal to 2 cosine theta. I don't have to write it because it's the same. So now integral dx is 2 cosine theta d theta divided by the square root is just 2 cosine theta. Oh, perfect. Theta plus c. So you can bring inverse sine as the answer. So sine inverse of x plus 1 over 2 plus c, or you can bring in the cosine. So inverse cosine of square root of 4 minus x plus 1 squared over 2. You can also bring that one, whatever. Really?
So in that case, we also get the theta from the Pythagoras, right?
Yeah, from here. Mm-hmm. Yes.
How about the integral of dt over 2 squared times root 225 minus 2 squared?
Like this?
Yeah.
It's another trig sub. Or 225 is 15. So when you set up your trig sub, you have your 15 over here, and you have t over here, and this on square root of 225 minus t squared. So when you set up your red and blue, remember they are circling the number every time. You have your red, which is sine theta, and the sine theta is t over 15. So t is 15 sine theta, and dt is 15 cosine theta d theta. And your cosine theta is the square root divided by 15, right?
Right.
So square root is equal to 15 cosine theta. So now, to substitute, dt is 15 cosine theta d theta. Now we need t squared. T squared is 225 sine squared. Nice. See, because you have a t squared over here and you have a t over here. You have to square both sides to make it a t squared. So you t squared and a square, so that makes it 225 sine. And then you have times the square root, and the square root is 15 cosine theta. So now this dies. 1 over 225 goes in front. Sine squared is a cosecant squared theta d theta. And the integral of cosecant squared is negative cotangent. And this is now the power of my method. You just look at the triangle and you pick up cotangent. Cotangent is adjacent over opposite. So negative 1 over 225. And the cotangent is adjacent over opposite, so it's a square root over t.
So you have to express it like that here, or we just do the cotangent of later?
Well, the integral is asking for x. Your answer must be x. You can leave answer theta. Like u substitution goes back from u to x, right? Trig substitution goes back from theta to t in this case.
And then everything except square the 15.
Ah, the 225 over here?
Yeah. And then it goes downhill from there. I started it, I was like,
Downhill?
yeah.
Why is downhill? You just have 1 over 15.
Yeah. After I get this part, I don't square that, but I square that. So that's
You're off by a factor of 1 over 15. It's not. The power is not wrong. It's minus 2. Yeah, the grade still. And it's minus 2 for carelessness. Because there's a federal law against that.
that, yes. I was going to do that.
Minus 2 better, right? Now, anything else?
How about a differential equation?
Of course.
Yes.
About 34.
So x squared dw dx is equal to
Square root of w.
and then 3x plus 1?
Yeah.
And does it have initial condition or no? That's it?
Correct.
Okay. So this is a differential equation, and this one is separable. You see a multiplication here, and you see multiplication here, which means all x's go on one side and all w's on the other. Now w, since it's in the numerator, has to stay on the left. So the square root of w will go on the left, and since it was multiplied on the right, has to go in denominator on the right, on the left. And the dx will go on top, so 3x plus 1 dx divided by x squared. So this is a separation of variables. When x squared that was on top goes on the right, it's going to go on the bottom. Dx was on the bottom, is going to go on the top. 3x plus 1 stays where it is. And then the square root goes on the left. So now what do I have? And I need to integrate this. So now I have the integral of w to the negative 1/2 dw is equal to the integral, and now you use integration techniques that you know. Now, when you have this situation, addition in the numerator, you simply divide this into 3 over x plus 1 over x squared dx. And you can integrate these now. So w to the negative 1/2 becomes w to the positive 1/2 divided by 1/2.
So would that part be the partial fraction? If you think about it that way.
It's not partial fractions, it's just now simple ln, right?
So I mean, for the other,
Because the multiplication.
kind of cut it in half.
I just split it because of the addition was in the numerator.
Oh,
Right? You can split. If it's in the denominator, then it's a partial fraction or something else. But when it's a numerator, you will split into 2 integrals. I could have written 2 different integrals. So the first one now is 3 ln absolute x, and then minus the integral of this is just 1 over x, right? And then you have plus c. So now you divide by 2 everywhere. So square root of w is equal to 3/2 ln x minus 1 over 2x plus c. That divide by 2 would absorb into c. And then you have to square everything to get w alone. Now you don't get to square it out, you just leave it as everything squared. Everything squared. You do not have to put plus c on both sides. When you integrate w, you don't have to put plus c because the other side has plus c. If you put plus c, then you have to put plus c1, and then, you know, they combine into overall. So you just put plus c on one side. You don't have to put on both. So algebra, in the beginning, to separate the variables. Put all of the same kind on one side and all of the other kind on the other side. And then you integrate. Integration is what? Partial fraction decomposition, or basic, or u sub, or by parts, whatever witchcraft we have to perform to solve the integral. But the key is to separate the variables, and then you integrate both sides. So you will always take the one that's in the denominator to the other side, and then just match the variables which way they go.
Why do you have to take one the denominator? Well, yes.
Dx, right? It's called the differential from Calc 1, right? Differential. We do the differential. Well, it's w1/2 divided by 1/2, but it's double fraction, so I bumped it 2 right away.
You scroll down a little bit. I want to see this C is inside. Okay, so C is inside it.
Yeah, because the square root of W, then you have to square everything, right?
What does it mean whatever you guys do?
Well, that's,
There's some of them by the one.
this is
Imaginary.
imaginary number I, 8, sum. Was special tonight because of this.
No, I don't need it still. I don't know.
Exactly. They just misspelled all of it, so, but it catches on. All right, good. Well, 2 days. Stop by tomorrow, right? I'll see you. Bye.